A very good afternoon to our supervisor, Dr. Wan Zairin, and our examiner, Dr. Noh Yu. This is Group 9 PDP2 presentation. My name is Perry. My group members are Ayman, Sidikin, Manbin, and Henry. Today, we are going to present our project titled Ammonium Sulfate and Methanol Production from Flue Gas. The problem that we are going to solve is the SO2 emission discharge that exceeded the maximum discharge limit. The objectives are design a plant that can reduce SO2 emissions below the maximum discharge limit, produce 2 value-added products, and include at least 2 reactor and 2 separation processes in unit operations. Moving on to market analysis in methanol, the figure shows that China demand of methanol is more than its supply, due to increased usage to create petrochemical products such as formaldehyde. Malaysia's strategy is to export methanol to China, which will reduce the gap between supply and demand of methanol in China. The market price of methanol is 0.45 US dollar per ton. Next, the market analysis in ammonium sulfate. In the figure below, shows that Vietnam demand of ammonium sulfate is more than its supply, due to high usage of ammonium sulfate in the farming sector. Malaysia's strategy is to export excess ammonium sulfate to Vietnam. This will help Vietnam to keep up with its demand in the agricultural sector. The market price of ammonium sulfate is 0.2 US dollar per ton. I will now pass the floor to Ayman to present his part. Thank you very much.
Thank you, Perry. My name is Aiman Azizi, and I will present about process screening and heat integration part. Okay, in process screening, we have 3 design alternatives altogether. All the design alternatives are consisted of flue gas desulfurization, CO2 capturing, and methanol production plant. In flue gas desulfurization, we have decided to use ammoniated water as our absorbent since it can directly produce our first value-added product, which is ammonium sulfate. So this process remains the same for all 3 design alternatives. In the first alternative, initially we have decided to use amine as our absorbent for CO2 capturing. However, due to the high operating cost and technical difficulties, we decided to change it to ammoniated water. The first and second alternative use direct CO2 hydrogenation, which is reacting CO2 with purchased hydrogen to form methanol. However, due to the lower yield of methanol and high cost of purchased hydrogen, it reduced our EP1 greatly. So we came up with the third design alternative as you can see in the slide. In the third design alternative, we introduced DMR in our process. So in the DMR process, in the dimethane reforming, the CO2 will react with methane to producing gas, which is carbon monoxide and hydrogen. So in the process, we actually produce our own hydrogen and purchase a few hydrogen for the CO hydrogenation, which is produce higher methanol yield compared to CO2 hydrogenation. So as the conclusion, we have decided to use alternative 3 for our process design, since we require lower investment in scrubbing agents, since we use both ammoniated water for flue gas desulfurization and also CO2 capturing, less hydrogen purchase since we produce some of our hydrogen, and producing higher yield of methanol since we use CO2 hydrogenation instead of CO2 direct hydrogenation. Due to this reason, it produces the highest EP1 compared to other alternative. Okay, moving on to the next part. So this is our PFD before heat integration. It consists of SO2 absorber, CO2 capturing system, dry methane reforming, and methanol reactor. We have identified 3 opportunities for heat integration as highlighted in the figure. For your information, the cold stream before entering a vessel or reactor required to be heated up by hot utilities. In order to reduce our hot utilities consumption, we decided to integrate the heat from the hot stream from the outlet of vessel or reactor. After performing pitch analysis using HIN software, we were able to match the required stream and calculate new utilities requirement for our plant. As you can see in PFD, after heat integration, we have added 3 unit of heat exchanger and add 2 cold utilities to certify the energy target for the hot stream. As a conclusion, we were able to recover up to 34% of energy for the whole plant, which save us up to 41.8 million US dollar per year for utilities. This sum up to 40% in terms of the overall cost reduction. That's all for me. I would like to pass the floor to Sidikin. Thank you.
Okay, thank you, Aiman. Now I will continue with PNID. So if you see the PNID, we have multiple control strategies. We have high selector here and we have split range controller here. More on that. For flash separator, we have recycle control valve CV506 and purge control valve CV505. So to maintain the driving force for recycle, a certain pressure is regulated by CV506. However, if the pressure gets too high, then when it reaches the breakpoint, CV506, the recycle valve will close, and CV505, the purge valve, will open to normalize the pressure. This is because if you don't normalize the pressure, it might affect the process. So next, result study for Note 1, we choose Note 1 for this presentation, includes SO2 and CO2 separation. If we see back the PNID, SO2 and CO2 separation, Note 1, means that everything that goes into the vessel and out of the vessel for CO2 absorber and SO2 absorber, here and here, is considered Note 1. So for parameter pressure, guide word more, deviation more pressure means that overpressure. The cause might be valve being half closed, valve fail closed, sorry. So means that there is no way for the material to go out of the vessel, so there is material buildup, or higher feed flow, because more volume will lead to higher pressures. So this might lead, the consequence might be vessel overpressure, and it might lead to vessel rupture. And safeguard is high pressure alarm, and action that should be taken is pressure safety valve or relief valve should be installed to depressurize the vessel in case of overpressure. Next, for plant layout, we have green area, which is low risk of fire and explosion. We have the yellow area, which is medium risk of fire and explosion, and red areas, the areas with high risk of fire and explosion. So the process area is situated near to the plant tower to reduce piping, and so is the case for control room, lab, and wastewater treatment plant and utilities. So the plant tower is situated in its own plot of land to ensure it meets the safety criteria for the clearance for safety radius around the plant tower. And storage areas is also put close to the process area to reduce piping. And expansion area 1 and expansion area 2 is provided to allow for future attachments. Now I give the floor to Manvin. Thank you.
Thank you, Siddiqui. My name is Manvin Dipko, and I'll be talking about major waste identification, regulation limits, as well as its treatment strategies. All the waste stream has been identified in Table 6.3.1 and 6.3.2 in our report. It is separated into gas and liquid streams. From there, for gas effluent, major waste is identified to be carbon monoxide, sulfur dioxide, and nitrogen dioxide, which are greenhouse gases and can cause climate change. Maximum discharge limits of all these gases are found in the Environmental Quality Act under Clean Air Regulation 2014. From the table above on the right side, it can be seen that sulfur dioxide and nitrogen dioxide does not require to be treated as it is already within limits. Carbon monoxide goes through gas flaring as shown in the diagram on the left. Assuming a 98% flaring efficiency as according to literature, after flaring, concentration of carbon monoxide is calculated to be 18.64 mg per meter cube, which is within limits and is shown on the right side table below. Similar to gas effluent, major waste for liquid effluent is found to be ammonia, and its discharge limit according to CAR 2014 is 20 mg per liter. Stream 30 does not require treatment. Stream 21 goes through treatment and reaches a concentration of 1.09 mg per liter, which is within limits. Treatment efficiency is assumed to be 85% from literature. In the wastewater treatment process, first, screening is done to remove larger and coarse solids like rags and sticks. Then, as shown in the block flow diagram, it enters the grid chamber to remove finer, heavier particles like sand, gravel, and separate oil and grease. In the equalization tank, flow rate is equalized to overcome operational issues caused by any flow rate variations. These processes are a part of pre-treatment. In primary treatment, firstly, primary settling occurs after the equalization tank. Suspended solid is separated with the help of gravity. Induced air flotation occurs in the tank where low density solids and oil and grease is separated from the liquid phase. Then, pH is adjusted to allow wastewater to adjust its solubility for it to attract to each other. Since ammonia is alkaline and sulfur dioxide is acidic, the wastewater is able to adjust its pH naturally instead of using external chemicals. Then, coagulation and flocculation removes emulsified oil, suspended solid, heavy metals, and a part of biological oxygen demand and chemical oxygen demand in suspended particulate form. This is done by adding coagulants and flocculants. Coagulation requires rapid mixing and flocculation requires slow mixing. Aeration tank is the start of biological treatment. In the aeration tank, colloidal matter and dissolved organic compounds like biological oxygen demand, chemical oxygen demand, and total suspended solids is treated by feeding them to microorganisms. Microorganisms uses dissolved organic matter as food source and converts all the waste into carbon dioxide and water. In the secondary clarifier, formation of activated sludge occurs in the water once all organic material is eliminated. Return activated sludge is recycled to the aeration tank to maintain the bacterial population, and waste activated sludge is eliminated. In tertiary treatment, chlorine is used as a disinfectant and is added to the water to kill pathogens that is left. Finally, clean water is able to be discharged. Sludge is sent into a thickener to reduce water content. It is then pressed and filled into containers before sending it to fertilizers manufacturers, which will produce organic fertilizers. That is all from me. I will now pass the floor to Henry.
Thank you, Marvin, and I'm Henry. And today I'm going to present about the process economics and cost estimation. Due to time constraint, I will make it compact and meaningful. So at first, we will have plant operation information over here, and we'll started off with calculating the capex and then to calculate the opex. So the plant is assumed to be 15 years lifetime, and starting off with the capex, we'll get our purchase cost of equipment, which this formula is obtained from CNOT 2019, and the values of constant are obtained from there as well. And then we'll calculate our PPC, which the PC is a compact, which the PC corresponds to this one, purchase cost of equipment, which is a compounded of those length factors over here, and then we'll get our PPC. And from there, we'll get our FCI from the PPC, which is multiplying by all this length factor, and which is compounded of all this length factor as well. And at the end we'll get our working capital. So from that working capital is actually 20% of our FCI, and we'll get our capex in the end, which is the summation of FCI with working capital. And because this capex is calculated, so we'll calculate the actual capex by adding up with extra 50%, and at the end the actual capex is 348 million. So after calculating capex, we'll get the OPEX, which is operating expenditure, and it consists of the variable operating cost and fixed cost. The fixed cost is divided into two parts. One is direct operating cost and the other one is indirect operating cost. So after getting all this, we'll get our OPEX as 792 million, and then we calculate our annual revenue. Revenue is what we have sold to the customer. So the revenue it comes from the ammonium sulfate and methanol, which are our product, and from this revenue we'll get estimated of 1 billion per year. And at the end we'll get our annual gross earning, which we subtract the OPEX from the annual revenue, and which the calculated value is 260 million. At the end, we also calculated our EP1, EP2, and EP3. The EP3 that we get is a value of 250 million per year, which is a positive value, and it is good to justify that our plant is economically feasible. And to further justify it, we use a payback period, which we calculated how much time do we need to get our money back. And with these assumptions, plant life of 15 years, plant construction period of year 0 to 2, and those material costs and operating costs are constant throughout the plant life, and annual income tax is 25%, and the minimum annual rate of return is 20%. We can get our payback period at year 4, and the rate of return that we have calculated is 39%, with a cumulative cash flow of 2 billion at the end of the plant life, and cumulative net present value of 836 million at the end of the plant life. So in conclusion, we'll start off with economic analysis that we get a positive EP3, NPV, and also cash flow in the end of project life, which is 15 years, and we get a payback period at the year 4, and also ROR is greater than MARR that we have assumed. ROR is 39% and MARR is 25%. With all this evidence, we can justify that our project is economically feasible. And just to recap, we have our plant capacity as 660k ton per year, and it is located at Ketek, Terengganu. And the final product quality of our ammonium sulfate is 90% and the methanol is 99%. And the heat degradation recovery rate is 34%. And also, in the end, we have our wastewater treated and our waste gas treated. Wastewater is treated from pre-treatment until the tertiary treatment, which is a conventional method, and the waste gas is removed through flaring. Thank you for your attention. That's all from me.